capacitive AC circuit. Now here in circuit, similarly to inductive and resistive circuit, here is only capacitor present in the circuit, and that capacitor, if we see the voltage across the capacitor VC, that is equal to supply voltage because of only one element in the circuit. The practical example, as we can see, the capacitor bank. Here we can see a lot of capacitors are connected to the system. So this is the case where we have to improve the power factor. Then this type of capacitor bank is installed at the premises. Here in our college also we have the capacitor bank to improve the power factor, which is there in the substation. In industry there is a lot of inductive load, so it will decrease the power factors value. To increase that power factor value near unity, then we need to install the capacitor bank. There is no other load in electrical system which only uses the capacitor. It is rarely used, right? So one example that I found, that capacitor bank, so we took here this example. Now voltage and current equations. Again, let us assume that the voltage which is starting from the origin, let us say it on a reference axis, so V is equal to Vc, that is equal to Vm sine omega t. Then we know the current in the capacitor, which is equal to rate of uh, rate of charge with respect to time, dq by dt. Then again we know the small charge q is equal to c into v, that q is equal to cv, the small charge and to small potential difference v, then q is equal to cv. So we have v is equal to vm sine omega t, so we can put it here pvm sine omega t. Then we can use this dq by dt in the above equation. So I is equal to d by dt, and the value of q is cvm sine omega t. Now let us take the derivative for this term. Here c and vm which are constant, then derivative of sine omega t, which is a cos omega t, and with respect to t, so this omega. So omega c vm cos omega t. Again we know we have to convert this cos omega t into the sine omega t. So cos theta is equal to sine theta plus pi by 2, right? So cos omega t is equal to sine omega t plus pi by 2. Then final equation we have I is equal to omega t vm sine omega t plus pi by 2. So we have adjusted in terms of the sine, because we have the original equation and the waveform is sinusoidal. We need to arrange in terms of the sine wave. By rearranging the above expression, what we get, rearranging this expression, what we get, I is equal to vm 1 by omega c sine omega t plus pi by 2. You get that. We have to arrange this omega c, so to get it the denominator, so it becomes 1 by omega c, right? So vm by 1 by omega c is nothing but im, and xc is equal to 1 by omega c, right? So final expression we have I is equal to im sine omega t plus pi by 2, where im is equal to, this is the capital I, im is equal to vm by xc, and xc is equal to 1 by omega c. So we have already stated this capacitive reactance, xc is equal to 1 by omega c. So this is the current in the purely capacitive AC circuit, where xc is the capacitive reactance in the circuit. So this is the derivation for the current that we got here, the angle omega t plus pi by 2. Now here it will be leading. In inductive circuit, what we saw, the current is lagging voltage by 90 degree, but in capacitive circuit it is opposite, current is leading voltage by 90 degree, right? So here we can draw the waveform, that the usual voltage waveform starting from the origin, v is equal to vm sine omega t. Now here in the current equation, omega t plus pi by 2, so it will be ahead of voltage waveform. So this is the point where current's waveform will start. So it will be ahead of pi by 2 to the voltage waveform. So we can show it. So the angle phi is pi by 2 or 90 degree, and with respect to that we can draw the phasor diagram. The voltage on the reference axis, then current is leading voltage by 90 degree or pi by 2. So here it is written. So this is the simple phasor diagram that we can draw. Now instantaneous power, which is again the same formula, T is equal to Vi. So we can put Vm sin omega t, Im sin omega t plus pi by 2, sin pi by omega t plus pi by 2, it is nothing but cos omega t. So Vm Im sin omega t cos omega t, we have this formula that is equal to sin 2 omega t by 2. We have arranged it here. So this is the instantaneous power, Vm Im by 2 sin omega t. Then average power, again it will be 0 because of sin 2 omega t. So this fluctuating quantity is present in the equation itself. So the average for this, for the complete cycle, becomes 0. So again in the capacitive circuit, the average power will be 0, and if you see the power waveform, so it will be same as that of the power waveform in the inductive circuit. So in positive half cycle, that the capacitor will get charged, and in the negative half cycle the capacitor will get discharged and energy will be given back to the source. So this process will be continuously happen, and the average power for the complete cycle, so it will be 0. So again in the capacitor it will not consume any active power, but it will consume the reactive power. Okay, the impedance in purely capacitive circuit, again the resistance value will be 0. Then impedance Z is equal to 0 minus j xc. Because why minus? Because x is equal to xl minus xc. This is the basic relation. So that's why the minus sign will be arises. So minus j omega j xc. Only imaginary term will be present here. And in the polar form, z is equal to xc angle minus 90 degree, which is in terms of the Ohm.